Good morning, everyone. So I want to start the presentation from now. The title of my presentation is given here, the fracture properties of the interlocking the structure by the Sickle joint printed with Strereolithography 3D printers. So I'm Masayuki Arai from Tokyo University Tokyo University of Science, so Japan. Here I want to talk about the background of this research is first. So one of the methods used to improve the fracture toughness of the brittle materials such as ceramics is the crack propagation path deflection. So this is an attempt to increase the fracture toughness by deflecting the crack propagation path away from a linear crack. Malik reported that Malik reported that the fracture toughness could be improved by introducing a jigsaw-like loops into the ligament ahead of the artificial crack in the CT specimen. The loops were processed by the 3D laser engraving and here. So this figure shows that the CT specimen with jigsaw-like loops, which was processed ahead of the artificial crack as shown here. So when we apply the external load for this CT specimen, the crack is opening around here, and then the tip of the crack is glued along the jigsaw-like loop as shown here. So which leads to that increases of the fracture area. The increase of the fracture area brings about the increase of that fracture toughness value following at the fracture propagation, crack propagation path deflection concept. So, and other researchers also have developed the different loop shapes and discussed the effects of the differences on the fracture toughness value. By the way, this picture is, the very famous temple that is the Holy Temple. Where is located in Kyoto, So when we construct this kind of temple, so joint technology was used in Japan to join the pieces of the wood as shown here together with Sickle joints as shown here, without using that nail. So this kind of joint technology based upon that interlocking mechanism that Saito can be applied. So the load was like this. So in this study, we focused on this kind of the Sickle joints the structure to increase the fracture toughness of the brittle materials. And so in this study, we attempt to increase the fracture toughness of the brittle materials by utilizing the interlocking structure created by this the Sickle joint. Here we investigated the deformation behavior and the fracture process of the CT specimens with the Sickle-shaped joint structure. The numerical analysis is performed using the finite elemental analysis, and also the tensor test performed on the CT specimen, fabricated using the Strereolithography 3D printers. So first, we want to show you that the CT specimen, the geometry with the Sickle joints ahead of the artificial crack as shown here. This is the CT specimen, and this is the Sickle joint parts. And then we printed this kind of the Sickle joint for these cases. So in order to discuss about the effect of the geometry of the Sickle joints on the fracture toughness, that the height of the Sickle joint as the shape parameter H was said to be 3.2, 40, 4.8, 6.4, 9.6, 10.4, and 11.2 millimeter for this the height of the Sickle joints. And also we prepared about the CT specimen with H equals 0, which consists only of the base metal. And also we constructed the finite elemental model based upon this shape. And also we fabricated the actual CT specimen by using that 3D printer. So after that, we conducted the tensor test for that. So the CT specimens were fabricated using the Strereolithography 3D printer. So in this study, we used the Form 3 plus form at the lab as shown here. And then the material was selected as the UV carbon resin in this study. And also the fabrication, the process is several steps to fabricate the 3D and the CT specimen in this study. And also this table shows that the process parameter for the 3D printer in the study. In this case, the layer pitch was said to be 0.05 millimeter, and also the laser power was 250 micron watt, and the laser aspect was 85 micrometer, and also the scanning speed was said to be 11 millimeter per hour in this case. So, and here we want to explain about the finite elemental procedure here. So and this is the FEM model, and then in this model, the elements the finally so divided around the Sickle joint around here, and those are the contact element were introducing around the interface of the Sickle joints. So in these cases, and also in this study, so the element was selected as that a triangular plane strain element model one here. And also as material conditions for this material of the CT specimen, that the Young's modulus was said to be 26 and 50 megapascal, and also the Poisson's ratio of 0.3. So those values were identified from that during the tensile test, and we compared that between the FEM results and then the tensile test results for the base metal. And also, in order to express about the crack initiation, the propagation, and the CT specimen, so the fracture was modeled by setting the peeling force between the elements as shown here. So for in this cases, that the peeling force sigma and normal to the edge of the element was said to be 100 megapascal. And also the one parallel to the edge of the element was said to be the 150 megapascal. So those parameters were identified from the comparing between the FEM analysis and the experimental observation result during the tensile test. So, and then the effect of the shape parameter H on the load displacement curve and the fracture process as investigates later. So here we want to show you that FEM result is, this is the contour plot of the measure stress and the deformation of the FEM model by applying the tensile load. So that this case corresponding to H equals 3.2. So starting so that the animation. So from this animation, after the slip deformation around the interface of that Sickle joint, the fracture occurs at the root of the female joint. So in these cases, on the other hand, so in this case, this is the case for the H equals 10.4 millimeter. So from this animation, along with the slip deformation of the Sickle joints, the plaque propagates towards the base metal of the female parts, and then the fracture at the roots. So, and this is the result for the load displacement curve obtained from the FEM simulation. First of all, so we look at the base metal data, which is shown as a blue line. When we look at the blue line cases, so that the load increases linearly with increases the displacements. After reaching to the maximum load, the load dropped sharply as shown here. So the from this result, is this base metal, it shows the brittle behavior. So during the fracture process. So for this case, it was found that the other cases of the H parameter, it was found that the elongation to the fracture increases with the shape parameter, the H. So, and also it can be the characterized from this result. It's that after reaching, oops. So after reaching that maximum load, it's the load decreases stepwise as shown here, regardless of the shape parameter and H. So from this FEM result, it was found that the high toughness can be expected by introducing the Sickle joint shaped interlocking structure in the CT specimen. So in accordance with the FEM result is here, so we conducted about the tensile test for the actual CT specimen, which was printed by the 3D printer. So this is the tensile testing devices prepared so in this study. Here, the CT specimen was set around here, and also during the tensile test, the specimen feature was continuously observed use the digital camera, and also the load load cell and this cross-cell displacement were recorded continuously into the data log as shown here. So the test condition, the cross-head speed was set to be a 10 meter per minute. That is a very, very low speed. So in comparison with the conventional speed of the tensor test. So we want to show you the continuous observation results for the actual CT specimen. This case corresponding to this is the case for the H equal the 3.2 millimeter. So for starting the observation results, so from this, the separation occurs only due to the SIP deformation along the sickle joint interface. There is no fracture in these cases. On the other hand, so when we look at the case for the H equal 10.4 millimeter, so from this the observation, the free parts, the broken at the smallest cross section of the joints, sickle joint, and then the base of the female part also the broken. That is a very complicated fracture behavior. So and the CT specimen when we chooses the higher age of the sickle joint parts. So on this result is summarized in the table for the all shape parameters condition. So from this, as the shape parameter increases, the fracture behavior changes as follows. Along the sickle joint interface, the penetrating the base of the female parts and minimum cross section of the male parts of the joint, sickle joints. Here we try to compare between the FEM and tensor test results. So in the load displayed curve. This the comparison reveals that unfortunately we found it that the effect of the sickle joint structure in the actual CT specimen was insufficient. So compared to the FEM results. So in this case, so this differences was caused by molding accuracy of the sickle joint in the actual CT specimen. Actually, so the female part and the male parts were molded separately and assembled before doing that tensor to set up the CT specimen. So maybe from this comparison, by improving the molding accuracy of the sickle joint in the CT specimen, it is expected that the fracture ductility will be the more improved. So from this experimental data. This is the final data. This is the relationship between the shape parameter H of the sickle joint geometry and fracture energy. Here, the fracture energy was defined as the area under the load displacement curve. So this red line shows that the film result here. From this result, the fracture energy was increases with the shape parameter H. So under the maximum, the value of the fracture energy was taken at the H equal 10 millimeter here. And after that, the fracture energy was exactly degrees as shown here. This is the FM result. This is ideal data for us. So and this is very comfortable for us. So, but so when we the double plot the experimental data on the same graph as shown here, this dot line shows that the experimental data. You see from this graph that there is a little bit of the differences between the experiments and the FM results and the fracture energies value. So, but from this, that we can say that there exists optimum shape parameter H for that which the fracture energy is maximized. So in the experimental data. But the fracture feature was quite different so in between the FEM and the experimental experiments. So and then so in this case, it's experimented in the experimental data, the maximum value of the fracture energy was taken at 8 millimeter of the shape parameter H. So from this, the FEM results show the higher fracture energy from this curve comparison, but improvements in the molding accuracy and sickle joint of that CT specimen are expected to further increase fracture toughness. This is the conclusion. Okay. Yeah. This is the I don't know read so this more, so, but this is a very important conclusion. The effectiveness of the sickle joint structure as a tendency to improve the fracture toughness of the brittle material was verified through this research. So it was expected that even greater the fracture energy could be obtained by first improving the molding accuracy using a 3D printer. That's all my presentation. Thank you very much.